Okay, sorry, missed a couple slides there, but we are still talking about Lewis acids and bases, and this is our goal number 1 of chapter 2. So thank you. I need to start writing that on a post-it note so I can see it before I start. Okay, so in this case, the first case was Arrhenius because we used water. The second case is a Bronsted-Lowry because we didn't use water, but we still transferred a proton, okay? Let's look at it one more time here, okay? So now let's start recognizing where we think those Lewis bases might be, okay? Now, and the thing I said to look for is look for lone pairs, okay? So in the case of the halide ions right here, once we form that halide ion, it becomes the Lewis base, okay? Because it has a lone pair that it can donate and create a new covalent bond, okay? It has a charge, so it already has the excess electrons that it needs to create that. And when it does bond, it creates a neutral molecule, okay? Now we call these very weak Lewis bases. And the reason we call those very weak Lewis bases is because they are very strong Bronsted-Lowry acids. Okay, so remember, a strong acid makes a weak base and a weak acid makes a strong base. We're going to see that trend follow in the Lewis acid-base system as well, okay? So all of our halide ions are considered weak, but they all have that lone pair to look for when you're looking for your Lewis base, okay? Next up is what we have are, notice they all have oxygen on it. Water, methanol, and ethers. Waters, alcohols, and ethers. They all have an oxygen on it, and the nucleophilicity of oxygen is driving why it is that base, okay? So it's less nucleophilic than the halide ions, but it only has the 2 lone pairs that it can play with, and because it can attract those protons, make a positively charged species, it is that Lewis base, but we consider them weak bases, and it all has to do with the nucleophilicity of the oxygen here, okay? Nitrogen has a higher nucleophilicity, or a lower nucleophilicity than that, but when we form those species here, we only have 1 lone pair that it can donate to be there, okay? So because it has 1 lone pair, it's a neutral molecule. It's considered a strong Lewis base. It's stronger than the oxygen-based nucleophiles, right? But notice it's also neutral because when we go to even stronger bases, they start to have the negative charge. They already have an electron. They're trying to, they already have excess electrons that they're trying to bond here. So notice the next highest one are oxygen-based anions, okay? Those are stronger than the neutral nitrogens, but they have charge, so that's what makes them stronger. And then our strongest form of our Lewis bases that we're going to use are going to be our nitrogen anions here, okay? So if you think about it, halide and then neutral oxygen, neutral nitrogen, charged oxygen, and then charged nitrogen, increasing in strength with each step, okay? Does that make some kind of sense to you? Okay, this trend we'll see time and time again, and they'll say, oh, well, I added this, but it didn't work. Okay, oh, you need to add a stronger base. So if you started with an amine and it didn't work, you now have to add a hydroxide or an alkoxide, which is the 2 charged species here. We'll talk about those more. Oh, it didn't work with that. Ooh, I gotta add a stronger base. So we have to go with these amide ions here. Okay, and we're going to see that when we start doing reactions is that some reactions will work with water. Some reactions will work with an amine base. Some reactions will require a hydroxide, and some reactions will require that amide ion. And it all has to do with that proton is less and less acidic, so you need a stronger and stronger base to fight it. Okay, good. All right. So I'm going to move to the next slide here, okay? So, like I said before, Lewis acids and bases are different than the Bronsted-Lowry because you must transfer a proton, okay? That's Bronsted-Lowry, and Arrhenius, you must have water, okay? So now I want to show you why we have to use the Lewis acid system when we're talking about organic chemistry. And the first Lewis acid I want to talk about is called the organic carbocation, which is a positive charge on carbon, okay? So let's think about this, okay? We have a positive charge on carbon, meaning that something has left and taken the pair of electrons that it was bonding to. And so it wants to accept electrons, remember acids accept electrons, to form a new covalent bond, okay? That's why the carbocation is a Lewis acid. It's accepting electrons to form that new covalent bond. And in this case here, we're using a very weak Lewis base, okay? Now what that means is this Lewis acid must be pretty strong to react with that weak Lewis base to create that new bond, to create our new covalent bond. This is that new covalent bond that formed reacting our Lewis acid and our Lewis base together. Okay. Now notice in this case here, the Lewis acid that we have here is a carbocation, meaning it has a positive charge, and this bromide ion had a negative charge. So we started with two charged species. By creating that new bond, we now have a neutral species, okay? So this can happen in a lot of cases. We can go with two charged species going to a neutral species. If we have neutral species, we'll end up going to a charged species. So we have to think about where the balance of electrons goes there. Okay, so this organic carbocation isn't a Bronsted-Lowry, and it isn't an Arrhenius. So that's why we have to use this new definition. And this new definition actually applies to all three systems. All right, good. All right. So when we're considering the relative acidity of these organic acids, we want to consider four factors, okay? And these are kind of in kind of decreasing order of importance, okay? So the electronegativity of the atom bonded to the hydrogen in the acid is number one. That's going to be a major contributing factor, okay? The second thing is going to be resonance stabilization. If you can stabilize that anion over more than one atom, it'll make that proton more acidic, that acid more acidic. And then the inductive effect, meaning that the atom itself is electronegativity is set, but you have other highly electronegative atoms that are pulling electron density away from it through at least one other bond. Okay, that's why it's inductive, because it has to pull through at least one other bond. And then the last thing is size and delocalization of charge. So this is most prevalent when we look at the halides. Fluoride ion is very small, chloride's a little bit bigger, bromine's a little bit bigger, iodine's the biggest of those ions, and as such, it becomes the most acidic of those ions, okay? So let's go and look at that in a little more detail. Okay, so electronegativity. When we start thinking about electronegativity, let's start thinking about just that number 2 row on the periodic table: carbon, nitrogen, oxygen, and fluorine, okay? Fluorine is the lowest electronegative of them, has the electronegativity right here of 4. Okay, then it's oxygen, nitrogen, and carbon in that order right here. So what we see here is that the pKa of HF, or having that, you know, the Bronsted-Lowry acid right there, is the lowest number, which means it's the most acidic, right? Remember, the pKa, the higher the number, the less acidic it is, the lower the number, the more acidic it is, okay? So then oxygen is next here, and this is just water. If you think about it, water itself is an acid. It can act as an acid or base. And so its pKa is around 15, okay? And then we have nitrogen, which is a little less electronegative. It means it's, you know, it's going to be less likely to give away that proton. This is a less polarized bond than this one and this one. So therefore, the acidity decreases. And again, the pKa value is going up, so the acidity is decreasing. And then the last one here is methane, methane here. That hydrogen on methane has a pKa of 51, okay? Now, if you think about it, that's not very acidic at all, because when we talked about that hybridization there, of the carbon-hydrogen bond, that's a very non-polar bond. It's not very polarized. And because it's not very polarized, that makes it also have a very, very weakly acidic. It's very difficult to pull that hydrogen off using a base, okay? So this is showing us that electronegativity of the atom the hydrogen is on controls the acid strength, okay? The next thing is the delocalization. And just like when we had the Lewis dot structures where we drew the carboxylic acid salt, or that carboxylate ion of acetic acid, we drew the acetate ion. When we drew that acetate ion, we drew one resonance structure where the charge is on one of the oxygens. We then drew the next resonance structure where the charge was on the other oxygen. And when we looked at resonance, we decided that neither one of these is a full representation of what's happening. And therefore, we had to have that dotted line going between this, where we have a partially negative charge on one oxygen and a partially negative charge on the other, okay? When we can do that, have that charge spread out over more atoms, that makes that hydrogen more acidic, okay? In direct comparison, in the carboxylate ion, we have oxygen. So our hydrogen is bonded to oxygen. And if we just looked at the electronegativity, then that would mean alcohol here might have the same acidity as the carboxylic acid right here, because they are both bonded to that same oxygen. It has the same nucleophilicity. But in the case of the alkoxide ion, once you have that hydrogen leave and those electrons are there, that charge is stuck on one atom and one atom only, okay? Because it can't be spread out, that makes it less acidic, okay? So the pKa value went up, making it less acidic, okay? So nucleophilicity isn't the driving force here now. We looked at nucleophilicity first, and now we're looking at resonance second. And having it spread out over more atoms makes it more acidic, okay? So I think that's kind of, you know, the next step of the puzzle here. Okay, and just like I said before, because our contributing resonance structures here can be on one oxygen or the other oxygen, in fact, it's probably spread out over both of them, that makes it more acidic, whereas we have a single resonance structure here. We do not have a contributing resonance structure at all. Therefore, it is less acidic. All right, now we have what we call the inductive effect. And the inductive effect is all about having high electronegativity atoms nearby, but not bonded directly to the atom that has the proton on it, okay? So in this case here, we have these fluorines right here, and fluorines are more electronegative than hydrogens here. Remember, fluorine is 4.0, hydrogen is 2.1 electronegativity. So these are twice as electronegative, okay? So, but if it was bonded directly to the oxygen, that wouldn't be an inductive effect. That would be a different type of bond. So in this case here, we have one bond, two bonds, and three bonds. The fluorine is that at least two bonds away. It's pulling electron negativity through this bond and through this bond, okay? So inductive effect is all about pulling electron density through one or more bonds away from the atom we're dealing with. And in this case, we actually have a total of three, and it goes and it increases the acidity. So we have the acidity of acetic acid without it. If we just add one fluorine to this, it actually drops down to about 4. If we add a second fluorine, it drops down to about 2. But by adding that third fluorine, we get almost down to 0. We're below 1 at this point right here. So each one of those fluorines has that inductive effect. We can actually monitor it by going 1, 2, 3. And so again, our lower pKa value means it's more acidic, and it's all because it's pulling electron density through bonds further away from the actual atom that has the hydrogen bonded to it, okay? Okay, so this brings us to our last thing, which is size and stability of the ion, okay? And so we typically look at the halides for this because when we have the organic anions, they tend to have resonance structures and spread out over more atoms. So when we think about the stability of the ions or the size of the ions, we're looking at the halides themselves because they are an atomic ion. Okay, they're not a compound. Okay, so when we look at that, we tend to think that iodine is the biggest of them. Then bromine gets smaller, smaller, and smaller. And if we think about that, it's because fluorine only has that 2 energy shell to have electrons in. Chlorine has a 3 energy shell. Bromine has a 4 energy shell, and iodine has that 5 energy shell. And remember, each of those shells completely encompasses the previous shell. So if we think of fluorine as very small, chlorine is going to be completely encompassing that with its shell, and then bromine is going to be completely encompassing that. So they're getting bigger and bigger and bigger. And so now you have 1 extra electron floating around this huge sphere, where in bromine you have that 1 extra electron getting a charge floating around a slightly smaller sphere. And then, so you can think about it as like that. You have 1 electron spread out over a small area in fluorine, 1 electron spread out over a huge area in iodine. And that's why iodine has the most acidic, because it can stabilize that charge over a huge area. So it's like, I don't need that hydrogen. I can just sit here and be a nice anion. Okay, so that is the size effect. Okay, let's see what this last thing is. Oh, that's the wrong slide for that thing. Okay, questions on chapter 1, goal 1. Chapter 2, goal 1. No, we're starting to get that. Now see why I did this first, because I wanted to talk about the way we're going to see acids and bases for the rest of the semester is all about accepting protons or donating protons. Bases accepting electrons and donating electrons, okay? Bases have the electrons to donate. Acids want to accept those electrons. That's what we're looking for, okay? Okay, I'm going to start with chapter 2, goal 2. Okay, so in chapter 2, goal 2, I wanted to describe the other acids because we still do transfer protons. So like things like methanol and HCl are still Bronsted-Lowry acids and bases. So that is still a valid way to look at them. However, they are it's not the most general class as the Lewis acids are. So, as I said before, the Arrhenius still falls under the Lewis acid because the proton, the hydrogen with no electrons around it, is accepting a pair of electrons to make the new covalent bond. And the water is the base because it's donating electrons, okay? Because Arrhenius has to have water to completely ionize the acid, okay? So Bronsted-Lowry, the acid is a proton donor, okay? Because the acid is still the one that's accepting the electrons to bond to that hydrogen to pull it away from its acid. The base is still a proton acceptor, but it is the one that has the electrons that's forming that new bond. So they both still apply to the Lewis acid base, okay? Oops, step. So, and remember, Arrhenius has to have water. So a lot of organic reactions, we don't have water. And we do them in non-aqueous solutions. So the Arrhenius definition doesn't really apply to most of our organic chemistry. And it completely ionizes in water. I'm going to skip over that. Okay, now in the Arrhenius bases, most of the time those are those inorganic bases. There are occasions where you do have hydroxides that don't have metals. And the one case that happens is in ammonia. Okay, so ammonium hydroxide is actually one of the few Arrhenius bases that does not have a metal counter ion. So In most cases, the Arrhenius has to have a metal counterion except for ammonia. We actually use ammonium hydroxide quite a bit in organic chemistry because it is fairly soluble in a lot of solvents. So we can use that as a base in our systems as well. Okay, so in this case here, just like we had, if we look at it as an Arrhenius kind of material, we're completely ionizing the material when it dissolves. And in this case, we still have our nitrogen acting as our Lewis base. The hydrogen, our water, is acting as our Lewis acid to generate our charged species that has the accepted proton that is that sharing that new covalent bond. And we've generated our new base here that can accept a proton from something more acidic. Okay. Okay. So again, in Bronsted-Lowry, we're talking about it has to transfer a proton, but it doesn't necessarily have to, it doesn't necessarily involve water. Okay, that's where Bronsted-Lowry steps away from that. And what we learned first in Bronsted-Lowry is that whenever we have an acid, it turns into a conjugate base, okay? Meaning once you transfer that proton, it now can accept a proton. That's why we call it the conjugate base, okay? Once we have a base that has accepted a proton, it now becomes the conjugate acid because it can transfer that proton back now, okay? That's one of the key values in Bronsted-Lowry that we have. So we always have these acid-base conjugate pairs, okay? Now, how far it goes to one side or the other, that gives us our equilibrium constant, okay? So things that like HCl, which are very strong acids, shift completely over to the chloride ion and the hydronium ion here. But as we learned, most of the acids have a pKa of above 0, which means that there's only a little bit is transferred to this side. And the higher and higher that pKa value is, the less and less of the material is shifted over to this product side. The more and more of the material is on the starting material side. Okay, and so this is the first example of where we can use Bronsted-Lowry without water, is with the reaction between acetic acid and ammonia to create our conjugate base of acetic acid, the acetate ion, and the conjugate acid of the ammonia, which is the ammonium ion. Okay, so then we're going to take that one step further and look at that equilibrium. Again, we are using the ammonia as our base. Our lone pair here is creating that new bond. That's this bond here. And we're taking these electrons. This oxygen is accepting those electrons and becoming our new Bronsted-Lowry base. Okay. So when we look at this, when we're thinking about this is actually kind of the opposite of the pKa chart, because we have the strongest acids on this side on the top and the weakest acids on the bottom here. But the trend of strong acids produce weak bases and weak acids produce strong bases is the valuable part of this chart, and the trend that needs to be kind of internalized as we go forward. Okay, conjugate acid pairs. The couple little things about that is that you can have more than one hydrogen transfer, so we can have multiple protons. HCl only has one proton to transfer. Carbonic acid has 2, and phosphoric acid has 3 protons that can transfer. Typically, when we do this, we generate negatively charged or neutral species. And then, yeah, that's the example of the carbonic acid, where when we first use water as the base here, we transfer 1 proton to create 1 hydronium ion, and you have the bicarbonate ion here, but it still has an acidic proton. So this can act as a Bronsted-Lowry base by accepting a proton and going back, or it can act as an acid with another equivalent of water as the base to generate the now completely deprotonating carbonate anion and another equivalent of the hydronium ion, okay? So that's one of the interesting things. This is why we think about things like buffers. In a buffer, you have an equilibrium created here where you've given away one proton, but it can accept protons or give away another proton, depending on what is available in there as the acid or base. It can be shifted back and forth by adding more water, adding more acid, and that's where we have that equilibrium constants. That's where we really start playing with those quite a bit and making them helpful for us when we look at the organic chemistry reactions. Okay, and of course the inverse relationship between acids and bases. Strong acid makes a weak base. Weak acid makes a strong base. That inverse relationship we're going to use again and again and again. Okay, questions on chapter 2, goal 2. Okay, I'm going to move to chapter 2, goal 3, and then we're going to be close to taking a break here. Oops. All right. So I want to talk a little bit more about pKa's and the conjugates, okay? Because knowing the general trend of pKa, knowing that the higher the number of the pKa, the weaker the acid is very important. We're going to use this time and time again. And knowing that once we deprotonate that acid, that if we had a pKa of 30, when we deprotonate that, that's going to be a stronger base than if we had something with a pKa of 20, okay? Because the 20 is the stronger acid, so it makes the weaker base, where the 30 is the weaker acid, so it's going to make the stronger base. And we have to compare those. But instead of having to worry about comparing pKa's and pKb's, which would be the base equilibrium constant, we're only going to look at the pKa, the acid strength, and its conjugate pair. Okay, so we're simplifying the system, so we only have to look for one value, and we only have to know the trends for one value. Okay, so a strong acid, of course, is one that completely dissociates in water, and we typically only use the inorganic acids for this, like HCl, HBr, HI, nitric, and sulfuric, and perchloric right here. And the strong bases tend to be only the ones that are ions of hydroxide. Okay, so the lithium, potassium, occasionally ammonia. So those are what we consider the strong acids and strong bases. Everything else, we're going to play with the pKa value to see where it fits in our scale. Okay, so we define weak acids as things that don't completely dissociate or don't completely shift to the ions, okay? So because they don't completely shift to the ions, there's that back and forth. And remember, the pK is our equilibrium constant of the acidity, how far back and forth that thing goes. And so by taking the log of that, the pKa gives us a nice tangible number we can play with, okay? So even when we do dissolve acetic acid in a large amount of water, you think having all of that water as the Lewis base, it would completely dissociate. But there's still a driving force for that little bit of that hydronium ion to reprotonate the acetate ion, which is the stronger base, that is a stronger base than water is, that it always shifts back a little bit, okay? So that's what a pK of anything above 0 is telling you, well, it's going to be a little bit of the undissociated acid always, okay? That's really what it means, and that's how we're going to use it, okay? So the general trend here we're actually going to start identifying these as we move through different functional groups even, but ethane right here, we can think of that as an sp3 hybridized carbon. That bond with the sp3 hybridized carbon is one of the least acidic things we are going to deal with in class, okay? So really the pK of 51 is almost the top of what we'll see in organic chemistry, okay? So we want to think of that as the weakest acid, okay? But that means that if we create a carbon with an anion on it, that means it's going to be very reactive because it's going to want to steal the proton from any other functional group below it, okay? Think of it that way. Think of it as if we formed this right here, it's going to steal a proton from ammonia, water, ethanol, phenol, benzoic acid, acetic acid. It'll steal protons from any of those, okay? So that's one way to look at this pKa chart, okay? The next way to look at this pKa chart is to say, okay, so I'm going to make a reaction with this compound here, and I am going to use a base to try to take that proton off, okay? So let's say I have that compound and I want to use a base. So because I see where it is on the chart, that means I can't use something like the ammonium ion to deprotonate this. I have to use something above it on the chart. So I have this carbonate ion and I want to take that last proton off. Well, I need to add water or ammonia or ethanol to be able to do that. So that's one way to look at this chart and use it to your abilities, use it to your advantage, is to think, huh, that didn't react. Oh, I need a stronger acid. I need a weaker base. I need to use it in that way, okay? And again, what I want you to remember about the pKa is not the absolute values here. We're going to build a chart. We're going to see the chart in the book, and I want you to know the relative values. Know that ammonia is more basic than water, and then ethanol is more basic, and so we have the different acid strengths that we can rack and stack, so that when we do reactions, it's like, well, if I add this to this, is it going to react? No, its acid strength is too high, or its acid strength is too low, just in a relative term. All right, questions on the goal 3, pKa's, relative pKa values, and the concept of the conjugate acid bases. Okay, all right, I'm going to take a break here then and stop sharing, okay? So what I can do here is I can stop recording this, and well, let me just stop recording right now.